Alright, we're going to get into the concept of hybridization and how it applies to organic chemistry, because it's actually pretty important. So let's say we got a carbon atom again. We know that this is in the atomic number of 6, meaning it's got 6 protons, therefore 6 electrons, and if we were to do an electron configuration, we start off with a 1s, 2s, and then we have our 2p orbitals, and so when we fill these, the electron configuration, here's the 6 electrons and where they belong. Now, one of the concepts that we learned is valence electrons. So the outer shell is the highest energy, the most energetic electrons. These are the ones that participate in bonding and will be involved in creating molecules. So keep in mind that this is an atomic orbital. And when a carbon attaches to another carbon, this is no longer, this on its own is an atom, and this is an atom, but together this has formed a molecule now. And if I've got hydrogens hanging off of it, we no longer speak in terms of atomic orbitals. We're now going to refer to molecular orbitals. And the molecular orbitals essentially are hybrids of the atomic orbitals. And specifically what we're going to pay attention to is the outermost orbitals that are involved. And so keep in mind that there is an S on the 2 level, there's a P, another P, and another P. And so the hybridizations that we're going to deal with are essentially hybridizations of these. So I'm going to define some terms in the next couple of minutes, but one of the things that I'll define is if we have 2 atomic orbitals that combine together, that's an sp hybridized orbital. Since there was 2 atomic orbitals, it'll create 2 molecular orbitals, and it'll have 2 atomic orbitals left over that can add to a double bond and a triple bond. If I combine together a s and 2 p's, we call this an sp2 hybridized orbital. This will create 3 molecular orbitals because there was 3 atomic orbitals involved, and there's 1 atomic orbital that would be left over, and that can carry out some double bonds. And then finally, if I were to combine all the s and the 3 p's together, this would be called sp3 hybridized, and what this does is it creates 4 molecular orbitals, essentially from the 4 atomic orbitals that were involved here. So we'll start from a carbon again, and we'll do something like methane. So if I have a carbon like this, and essentially I've got the 4 atomic orbitals, so I have the 2s, a 2p, another 2p, and another 2p. And essentially what I'm going to do is I'm going to combine all 4 of these atomic orbitals to create 4 sp3 hybridized molecular orbitals. So I have 4 of these. So if I take a look at carbon, what I'll have is I can draw them like this. There's 1 orbital, a little node down here, 1 orbital, another orbital, and another orbital. So there are 1, 2, 3, 4 molecular orbitals that have been developed from the 4 atomic orbitals. And so this carbon can now bond to another atom in a molecule in this fashion. So if I were to, for example, take hydrogen, hydrogen would attach onto this orbital, hydrogen would attach onto this orbital, hydrogen would attach onto this, and hydrogen would attach here. So you can see I have the 4 hydrogens. The orbitals essentially are where my electrons can reside, like this. And so I've got a complete overlap of all the orbitals, and this is essentially called a hybridized molecule. So I can redraw this if I want as a C, just with the lines, like this. Now one thing to notice is I haven't evenly drawn all the hydrogens around this carbon. That's because when we take a look at the molecular orbitals, this actually starts to imply shape to the molecule, and that's why we need to learn about hybridization first before we get into shapes. So if I have an sp3 hybridized atom like carbon, I will have 4 single bonds to it, and the single bonds are going to be evenly spaced around each other. So this bond angle here, this bond angle, this bond angle, and these bond angles here are all going to be 109.5 degrees away from each other, so evenly spaced. And we also call this molecule a tetrahedral. So if we find a carbon that's a central atom, if the carbon has 4 single bonds surrounding it, we can say that that was an sp3 hybridized carbon, and we can also imply that there is a tetrahedral shape to that atom, or the atom surrounding that central atom. Continuing with the tetrahedral type shape, we're going to take a look at nitrogen. So if we have nitrogen like this, so rather than having carbon as the central atom, I'm going to have nitrogen, and this is ammonia. This is a full octet around nitrogen, 2, 4, 6, 8 electrons around it. I have 3 single bonds, but I have a lone pair of electrons. So in the case of nitrogen, the nitrogen here is sp3 hybridized as well. So in essence, what it has, the nitrogen, is 1 sp3 orbital, 2 sp3 orbitals, 3 sp3 orbitals, and another one up here. This is the same, essentially same tetrahedral shape as with methane, but we no longer call it tetrahedral because I will have a hydrogen down here, a hydrogen attached here, a hydrogen attached here, and the lone pairs are up here. Because I've only got the 3 atoms attached down below and this lone pair, this shape kind of looks like a pyramid, and so we'll say it's a pyramid shape. And now we can move on to something like oxygen. So let's say we've got oxygen as our central atom, and we'll take, for example, water. So here water it's got only 2 atoms attached to it. It has 2 lone pairs. The oxygen has a full octet. It only has 2 lone pairs of electrons and 2 single bonds. The oxygen here is sp3 hybridized, meaning if I have the oxygen here, I'm going to have an sp3 hybridized orbital here, one here, and one up here like this. The hydrogen will be attached, 1 hydrogen to each of these sp3s, and in the leftover sp3 orbitals are those lone pairs that we're looking at. So these lone pairs here actually occupy one of the molecular orbitals, one of the sp3s. So there's an sp3 molecular orbital here, sp3 molecular orbital here, sp3 here, and an sp3 here. 4 molecular orbitals. So in essence, what we call this then is a bent shape. So if we don't take into account the overall shape here, we originally say this is a tetrahedral initial arrangement, but because there's only 2 atoms here, we don't call it tetrahedral, we will call it a bent shape, just taking into account the atoms. So this is the bent shape that occurs out of it. So when it comes to an sp2 hybridized atom, we'll take carbon as an example again. So if I have my 4 atomic orbitals, an sp2 hybridized molecule has 3 atomic orbitals combining together to create 3 molecular orbitals, and we're going to have 1 atomic orbital left over, so atomic p orbital, and we'll get to that in a sec. So if I were to evenly disperse the molecular orbitals, I have 1, 2, 3 molecular orbitals surrounding carbon, and these get evenly dispersed. Now imagine that these are in the plane of the page, and they form a triangle. So essentially these are, the shape typically from this is trigonal planar, meaning they're in the page. And what happens is that this extra orbital left over now comes sticking out of the page. So this is a p orbital, and it's tough to see, but this part here would be coming above the page, and this part here is below the page. Okay, so it's kind of like this 3D shape that occurs out of it. So I'll redraw it again. There's the carbon. There's one of the sp2 hybridized orbitals, another sp2, another sp2. And if I were to, for example, have a hydrogen attached here, a hydrogen attached here, and I could, for example, have a carbon attached here, like this, in another hybridized orbital. So what this accounts for, or what this shows, let me just redraw this again here. Get the carbon as another. If I had another carbon here, and this was also sp2 hybridized, these two orbitals would overlap. So this is an sp2, this is an sp2. And what I told you here is that there is a p orbital left over. So the p orbital now is free to interact. And if this carbon was also sp2 hybridized, it also has a p orbital free to overlap. And so now this is a secondary interaction. This bond right here is a full overlap. This is called a sigma overlap. This bond here is now called a pi bond. And this constitutes a double bond between a carbon. So if I were to show this to you, an ethene molecule, you might understand this a little bit better. Here's a double bond, here's the hydrogens attached. But the actual molecular orbitals that are involved in this, this is it here. So this carbon has 3 sp2 hybridized orbitals. One here, one here, one here. So 3 sp2 hybridized orbitals. And it has an extra p orbital. And that p orbital, the extra p orbital, allows for this secondary overlap. So this pi bond to actually occur. So the same thing that can happen on this carbon. It's sp3 hybridized. Because it's sp3 hybridized, I have 1, 2, 3 molecular orbitals. I have 1 p orbital left over, and that allows me to create this double bond structure here. So to redraw it again, because it does get very messy, essentially like that. So the general rule of thumb is if you see a double bond, the atoms are sp2 hybridized, and I'll show a couple of examples of that. Okay, so we've seen the one example where we've got a carbon-carbon double bond. So as soon as we have a double bond involved, this is that carbon is an sp2 hybridized carbon. And this will become important later when we get into shapes, understanding this. And even the line drawing concept comes from the hybridization theory. But let's say we've got, for example, a compound that looks like this. So this is formaldehyde. This is a trigonal planar shape to it. The carbon here, because it has a double bond, we can assume right away, one double bond associated, that it's sp2 hybridized. But so is the oxygen. The oxygen in this case is also sp2 hybridized. If I were to draw, for example, benzene, and I have all these double bonds, this carbon is part of a double bond structure, and this carbon is part of a double bond structure. So this carbon would be sp2 hybridized. This one is sp2 hybridized. This carbon is part of a double bond structure. This one is part of a double bond. This is part of a double bond. This is part of a double bond. So one of the reasons why benzene is so unique is because all of the carbons are sp2 hybridized, and that makes it quite unique. Let's say, for example, we put nitrogen in. So we'll take something like this, and we've got nitrogen involved. So a couple things we have to pay attention to. One, we have to make sure the octet is fulfilled for everything. So If we have carbon here, we've got 1, 2, 3 bonds. The implication is that there's a hydrogen here. There's a double bond on this carbon. This carbon is sp2 hybridized. This nitrogen has a double bond as well. It has 2, 4, 6 electrons around it, and so what we have to do is also imply that hydrogen is on it as well. But for drawing conventions, the heteronuclear atom always shows the hydrogens attached implicitly. Carbon doesn't have to, but heteroatoms always have to. So if oxygen had a hydrogen on it, we'd have to show it. If nitrogen has it, we have to show it. So this nitrogen is also sp2 hybridized because it's part of this double bond structure, and it would have an extra p orbital left over to create this double bond. And finally, we will get to a triple bond, or sp hybridized carbon. So if I have a carbon and I've got my atomic orbitals, I'm just going to use these two atomic orbitals to combine to create two sp molecular orbitals. And that means I have two p orbitals left over, so two p atomic orbitals are left over. So if I have a carbon, I have one sp orbital, one sp orbital. So if I had a hydrogen on this side, I can form a sigma bond there. If I had another carbon here, I could have an overlap like this, and I form an overlap and I form a sigma bond. So down below, this would look like a hydrogen, a carbon here. If I had the other sp orbital here, it would look like that. And there's my hydrogen. But if we're taking a look at the octet, so there's 2 electrons there, 2 there, I'm missing 2 electrons, but I have no more atoms to add to it. And so what happens is I have got these 2 extra p orbitals left over. So one p orbital will be in the plane of the page. So this will be flat. And this is one of the bonds I just showed with the sp2. So this was a sigma bond. This is a pi bond. I'll call it pi 1 because we have 2 p orbitals. So there's a second p orbital that's perpendicular to it. This is actually drawn technically in 3D. So this orbital is coming out at us. This one's coming out at us. And the other mathematical representation of it is on the other side. And that creates another pi bond. And I can call this pi 2. So what that looks like then, I'll draw it up here, see if I can make it look prettier. I don't think I will. So there's pi 1. There's pi 2. And the sigma bond. That's 1, 2, 3 bonds. So this is a triple bond. So if you were to see a triple bond involved, this is the carbon associated with it is a sp hybridized, and so is the other carbon. And it's not unique to carbons. It can also happen with nitrogens. So if I were to have a carbon and I have something like acetonitrile, this carbon is sp hybridized because it's attached to a triple bond, but so is this nitrogen. So this nitrogen is also sp hybridized as well. There's one unique structure that occurs that's sp hybridized for a carbon, and I'll show you in a second. It looks like it's a double bond, but it's actually 2 double bonds together, and it creates an sp hybridized molecule. So this is the molecule here. It's an alene molecule, so it's unique in that it's got 1, 2, 3 carbons associated with it. If we were to rotate this around in a sec, I'll show you the 3D shape, but this carbon here is an sp2 hybridized carbon. The carbon on the other end is sp2 hybridized, and the carbon in the central is sp hybridized. I would draw this out, but it's a little more difficult for me and it gets pretty messy, so I just thought I'd do some pretty pictures. But I can rotate around with this program here, and we can actually see then I don't have it optimized yet. Here we go. Hopefully this works now. So there we go. So rotate that around and you can see the structure. I'm just using ChemSketch here from ACD Labs. It's a free software. And you can actually create these compounds, turn them into mol documents and put them into a mol reader. And they will show you the rendered 3D shape as well. Anyway, this is, so again, an sp2 hybridized carbon here, sp hybridized carbon, sorry, sp2 hybridized carbon here, and sp hybridized carbon in the center. And I'll show you now the molecular orbitals on a picture. And this is the pretty picture that I was referring to that I just can't draw as nice as this. But essentially it indicates here that the central carbon is sp hybridized. The N carbons are both sp2 hybridized. So we're combining here one s atomic orbital and two p atomic orbitals to create three sp2 hybridized molecular orbitals. One of the sp2 hybridized orbitals is used as a sigma bond to hydrogen. Another one is used as a sigma bond to this hydrogen, and the other sp2 is used as a sigma bond towards this carbon. Similarly, on this carbon, an sp2 hybridized orbital for sigma bond here, and a sigma bond here. So in each case, this would give one of those double bonds you would see that's typical in an alene. Now we need to find the other bond to create the double bond. And so that's where the leftover p orbital comes. So this atomic p orbital that's left over on carbon and the atomic p orbital that's left over here are used to create that double bond with the carbon next to it. And the problem is that the central carbon, it needs to have an extra p orbital to bond to this one, but it needs a different p orbital to bond to this one. And so what happens is these two p orbitals being perpendicular to each other, the hydrogens actually end up sort of in a different shape. They're perpendicular to each other. So this forms like a trigonal planar shape right here. And this also forms a trigonal planar shape, but these two are perpendicular to each other because of these p orbitals being forced to be perpendicular to each other like this. So it's a very unique situation where this carbon, even though it looks like a double bond on either side, is actually sp hybridized.